In our previous lectures, we have already discussed about the crystal structures, interatomic bondings, about the metals, ceramic, polymers and some kind of advanced materials. Today actually we are going to discuss about the introduction to X-ray diffraction. So, before going to start about the X-ray diffractions, let us know what are X-rays. So, X-rays are the electromagnetic radiations of exactly the same nature as light, but of very much shorter wavelength. X-rays used in diffraction have wavelengths lying approximately in the range of 0.5 to 2.5 angstrom. X-rays occupy the region between the gamma and UIB rays in the complete electromagnetic spectrum, that I will show you later. They are produced when any electrically charged particles like electrons of sufficient kinetic energy is rapidly deaccelerated. So, here the beam of electrons it is coming hitting the target, and then from that the X-ray is generating. So, what are the properties of X-ray? First, X-rays travel in straight lines at the speed of light. X-rays uncharged or neutral particles cannot be deflected by any electric or maybe the magnetic field. They affect the photography film, then they can produce the fluorescence and the photoelectric emissions, and also they can penetrate the matter. Penetration power is least in the materials of higher density. So, this is known as the electromagnetic spectrum. So, left hand side the top is known as the X-ray wavelength, which is nothing but 0.5 to 2.5 angstrom, which I have already told. Generally the visible light wavelength is 6000 angstrom. So, penetrating power of X-rays is more than the ordinary light. And if we see carefully the electromagnetic spectrum, so we can find the X-ray is lying over here. So, X-ray the radiation type wavelength is 10 to the power minus 10 meter, and this way the energy is increasing. So, after that X-ray it is only followed by gamma ray. So, now we are going to discuss about the generations of X-ray. So, X-ray generally it is we are doing it into some test chambers. So, first we are talking about the evacuated glass tube, which allow the electrons strike the target without collisions with the gas molecules. So, right hand side picture you can see that this is known as this black in color is known as the evacuated glass tube. Inside that glass tube you can see that heated filament over there, the target is there and some water cooling systems are there. So, how it is actually occurring? So, first heated filament, which is nothing but known as the cathode, made from the material of lower ionizations energy. So, this is known as the cathode over there. So, now we are having the target, or it is sometimes it is called the anode also, anode material made from heavy metal of high melting point like molybdenum or maybe the tungsten. So, this is our anode materials. Then we are having some cooling systems, because when the X-ray is generating, the heat as well as the X-ray ray both are generating. So, that anode material should not be melt. So, that is why we are using some kind of cooling arrangement over there, so that the anode material should not melt. Now, we are having another high voltage source, which is nothing but used to set the anode at a large positive potential compared to the filament, so that all the electrons should be attracted towards the anode. So, when a filament is heated by current supplied to it, many electrons are emitted by thermionic emissions, which means emission of electrons from a heated conductor. These electrons are accelerated in vacuum by a high electric field in the range of 20 to 60 kilovolt towards a metal target. High speed electrons strike the target and their kinetic energy transferred into heat energy and the X-ray radiations. So, this is the simple image that through that the electron it is generating, then it is hitting your target materials, and through that the X-ray formation is taking place. So, now there are actually two types of radiations by the X-ray tube. One is called the continuous X-ray, another one is called the characteristics X-rays. So, what is known as the continuous spectrum? Generally the continuous spectrum taken care by the heat energy. So, most of the kinetic energy of electrons is converted into heat energy of electromagnetic radiations, which is nothing but the kinetic energy is equivalent to electromagnetic radiations, which is nothing but the half mv square is equal to hf. So, here only less than 1% being converted into the X-ray, that means except 1%, this 99% is converting into the heat energy. So, X-ray is coming from target have a mixture of different wavelengths. The intensity is 0 up to certain wavelengths called the short wavelength limit, which is denoted by generally that lambda SWL. Smooth curves are also called the heterochromatic continuous or maybe the white radiations. So, from this particular figure you can see that we are getting some smooth curve over there. So, which is nothing but known as the white radiations, and this point actually it is known as the short wavelength. So, the intensity in this particular point is 0. Now, we will discuss about the characteristic spectrum. So, what do you mean by characteristic spectrum? So, when voltage on an X-ray tube is raised above a certain critical value, characteristics of the target metal sharp intensity maxima appear at certain wavelengths superimposed on the continuous spectrum. Since they are so narrow and since their wavelength are the characteristics of the target metal used, they are also called the characteristic line. These lines fall into several sets referred to as K, L, M. These actually all are the shells in the order of increasing the wavelength, all the lines together forming the characteristic spectrum of the metal used as the target. So, actually after doing that one, whatever the characteristic peaks are coming or maybe the characteristic peaks are forming, they are actually superimposing onto your white radiations or maybe that normal peaks. So, in this particular case, if you see this particular graph, you can find out that the x axis is denoting the wavelength and y axis is giving the intensity, and this zone is known as the continuous line is known as the white radiations, and then after that we are getting some kind of characteristics radiations like K beta, K alpha. So, here you can find some peaks are broadened, some peaks are so sharp. So, these all are known as the characteristic peak. Now, characteristics X-rays. The characteristics line in X-ray emission spectra corresponding to atomic electronic transition where an electron jumps down to a vacancy in one of the inner cells of an atom. So, from this particular case you can see initially it has been started with the M cell, then it is jumping to the L shell and then it is jumping to the K cell itself. So, the electron is jumping from one shell to another. Such a hole in an inner shell may have been produced by bombardment with electrons in an X-ray tube. So, when the electrons is jumping from one shell to another cell, so generally the emissions of the X-ray is taking place, but generally we prefer that electron is jumping in the inner cell so that its intensity will be more. So, now X-ray sources with different lambda for doing XRD studies. So, here it depends upon the different target metals. If we talk about the molybdenum, so lambda for K alpha radiations is 0.71, for copper it is 1.54, for cobalt it is 1.79, for iron it is 1.94 and for chromium it is 2.29. So, only as I told already, only K lines are useful in X-ray diffraction as the longer wavelength line being easily absorbed. So, generally we prefer that electron should jump from K shell to the L cell. Only 3 strongest radiations are observed in normal diffraction like K alpha 1, K alpha 2 and K beta 1. Use of filters. So, now we will discuss about the filters. So, in this particular case actually what happened, we are getting so many peaks over there, but some peaks are due to the temperature, some peaks is due to the material characteristics, some peaks is due to the different radiations. So, now actually we are using certain kind of filters to get the actual crystal structure or maybe the actual crystal informations of that particular materials. So, choose for the filter an element whose K absorption edge is just to the short wavelength side of the K cell lines of the target material, so that it can eliminate the other sources. So, generally K beta and K alpha 2 will cause extra peaks in XRD pattern, but can be eliminated by adding filters. So, that is why we are adding filters just to restrict the other spectra over there. So, in this particular figure you can see that when you are using no filter, so we are getting K beta as well as the K alpha, but in this particular case the K alpha is required for us. So, that is why you are using certain kind of nickel filter. Due to that the K beta radiation has been suppressed and we are getting only the K alpha radiations. So, comparison of the spectra of copper radiations before and after passage through a nickel filter. The dashed line is the mass absorption coefficient of the nickel. So, this is the mass absorption coefficient of the nickel filter. So, which are the factors which affects the X-ray spectrum? First one is called the tube current, then tube voltage, added filtration, target material and the voltage waveform. Now, let us come to the actual point that why X-rays are used in crystallography. So, for electromagnetic radiations to be diffracted, the spacing in the grating refers to a series of obstacles or a series of scatterers should be of the same order as the wavelength, so that X-ray can easily pass through that gap. In crystals, the typical interatomic spacing generally it is 2 to 3 angstrom. So, the suitable radiations for the diffraction study of crystals is X-rays. If the wavelength is of the order of the lattice spacing, then diffraction effects will be prominent. Hence, X-rays are used for the investigation of the crystal structure. So, nowadays for any characterization of about the crystal structure for any known materials or maybe the unknown samples or maybe the unknown materials, the X-ray diffraction study is the vital one. Three possibilities exist based on the wavelength lambda and the spacing between the scatterers A, like if lambda is less than A, the transmission dominated. If lambda is equivalent to A, the diffraction dominated, and if lambda is greater than A, then reflection dominated. Now, we are going to discuss about the interaction of X-rays with the matter, means the materials. So, first I have told you that incident rays it is coming to the specimens, and then generally it is divided into 5 parts. One is called the fluorescent X-rays, then scattered X-rays, transmitted beam, electrons and the absorption or maybe the heat. So, scattered X-rays also is divided into 2 parts. One is called the coherent from bound charges. So, which is nothing but the known as the XRD or maybe the X-ray diffraction. Another one is called the incoherent or maybe the Compton modified from loosely bound charges. And if we talk about the electrons also divided into 3 parts. One is called the Auger electrons produced by loosely bound electrons. Another one is called the Compton recoil produced by strongly bound electrons. Another one is called the photoelectrons, which is nothing but the knocks out electrons. So, generally X-ray can also be refractive index slightly less than 1 and reflected at very small angles. Now, we are going to discuss about the different X-ray sources with different lambda for doing the XRD studies. So, generally we are using copper as it is because it is widely used. So, sometimes we are using the silver, molybdenum or maybe the cobalt also. So, here you can see that what is the energy value and what is the lambda value for K alpha 1, K alpha 2, K and K beta and K beta filter, means after using the filter that what the value we are subtracting from it. So, if we talk about the copper, because I am giving the example copper because it is widely used. So, generally the lambda of K alpha 1 radiations is 1.540598 and lambda of K alpha 2 radiations is 1.54439 and lambda of K beta radiations is 1.39222. So, generally here we are using the nickel filter whose value is 0.017. So, generally that 0.017 value has been subtracted from the lambda value and only we are getting the copper K alpha value and which is we are using for our X-ray diffraction studies. Now, let us discuss about the diffraction. What is diffraction? So, diffraction refers to the apparent bending of waves around small objects and the spreading out of waves past small apertures. In our context, diffraction is the scattering of a coherent wave by the atom in a crystal. A diffraction pattern results from interference of the scattered waves. So, actually the thing is that when something it is hitting onto that materials, the materials actually it is giving some coherent wave from by the atoms when there is in a particular crystal structure. So, the electrons in an atom coherently scatter light when we can regard each atom as a coherent point scatter, the strength with which an atom scatters light is proportional to the number of electrons around the atom. Another point is that the atom in a crystal are arranged in a periodic array and thus can diffract the light. The scattering of X-rays from atoms produces a diffraction pattern which contains informations about the atomic arrangement within the crystal. Amorphous materials like glass do not have a periodic array with long range order, so they do not produce a diffraction pattern. Now, what is the basics of the X-ray diffractions? So, X-ray diffractions, first, one of the best methods of determining a crystal structure, which I have already told you. In macromolecular X-ray diffraction experiments, an intense beam of X-ray strikes the crystal of study. In general, crystal diffracts the X-ray beam differently depending on its structure and orientations. Yes, of course, because it varies from material to material and about their atoms. The diffracted X-ray is collected by an area detector. The diffraction pattern consists of reflections of different intensity which can be used to determine the structure of the crystal. However, many different orientations of the crystal need to be collected before the true structure of the crystal can be determined, because in a material, maybe if it is a composite or maybe some other materials or maybe some impurities can be present. So, there are so many types of elements can be present and all the elements is having different diffraction pattern. So, from the right hand side image you can see that from the X-ray tube the X-ray has been generated, then it has directly fallen onto the crystal or maybe on the material, and then after diffraction it is having some shielding arrangement. Through that shielding directly it is going on to the photographic plate and it is giving into some dot dot structure by which we can get the crystal structure of that particular materials. Now, we are going to discuss about the diffraction phenomenon. So, generally diffraction is a consequence of specific phase relationships established between two or more waves that have been scattered by the obstacles. Maybe sometimes they can be together or maybe sometimes they can be overlapped. So, diffraction occurs when a wave encounters a series of regularly spaced obstacles that are capable of scattering the wave and have spacings that are comparable in magnitude to the wavelength. Diffraction requires three important conditions to be satisfied. First one is known as the coherent, monochromatic and the parallel waves. Second is that crystalline array of scatters, and the third one is called the Fraunhofer diffraction geometry. So, in the right side also you can see that when we are talking about the single slit diffraction, so here it is showing the multiple sources, but it is going into in a single way. But when you are talking about the double slit diffractions, so you can see that the light wave when it is falling onto the materials, and then after that all the signals it is actually they are mixing all together, but for the single case you can get only a single signal over there. Not all objects like scatterers for all kinds of radiations. If wavelength is not of the order of the spacing of the scatterers, then the number of peaks obtained may be highly restricted. In short, diffraction is coherent reinforced scattering or reinforced scattering of coherent waves. In a sense, diffraction is nothing but a special case of constructive or maybe destructive interference. To give an analogy, the results of Young's double slit experiment is interpreted as interference, while the result of multiple slits like large number is categorized under diffraction. Fraunhofer diffraction, what it is telling about? Fraunhofer diffraction geometry implies that parallel waves are impinging on the scatterers, means on the object, and the screen to capture the diffraction pattern is placed far away from the object. So, the distance is more in this particular case. Now, we are talking about the effect of the path difference. So, first we will discuss about the optical interference. So, difference in the length of path travelled lead to differences in phase. The introduction of phase difference produce a change in amplitude. Summed amplitude of the waves can have any value between 0 and the sum of the individual amplitudes. So, when we are talking about the constructive interference, so in this particular case you can see that in this particular phase generally the n value is coming around 0, 1 or 2, n means nothing but the order and delta is the path difference. So, in this particular case you can see that we are getting certain value into different phases, but when you are talking about the destructive interference you can see the value is always 0 over there. So, perfectly out of phase, first it is out of the phase. So, that is why it is known as the destructive interference, n value is half or maybe 3/2 or maybe so on. Now, we are going to discuss about the Bragg's law. It is the law has been discovered by a famous scientist, and this law is very essential to measure the interatomic distance of any materials or maybe any other unknown or maybe the known samples. So, their famous law is known as the Bragg's law. It states the essential condition which must be met if diffraction is to occur. So, what is that law? Which is nothing but the n lambda is equal to 2d sin theta. So, here n is called the order of reflections, it may take on any integral value consistent with sin theta not exceeding the unity and is equal to the number of wavelengths in the path difference between the rays and the scattered by the adjacent planes. So, when Bragg law is satisfied, reflected beams are in phase and interfere constructively. So, that means we can get the results. So, right hand side image you can see that when the rays are coming, because rays is not a single one, there are so many rays are coming together. So, when we are talking about the ray 1, it is falling in this particular point and then it is reflecting in these directions. So, when it is falling, it is creating some angle theta over there, and with same angle also it is going back after scattering. Then when we are talking about the ray 2, it is falling here, but you can see when you are talking about the ray 3, ray 1 and ray 3 the plane is same, but when we are talking about the ray 1 and ray 2 the planes are different. So, now how to calculate the path difference over there? So, when we are trying to calculate the path difference of ray 1 and ray 2, from this you can see that when ray 1 is coming at an theta angle and it is going back also into the theta angle. So, if we put a perpendicular line from this P point, so this is known as the Q point over there. So, we are doing the Q. Now, when we are talking about the ray 2, from this K point we are making a perpendicular on R. So, what will be the path difference over there? For rays 1 and 2 the path difference will be QK, Q and K over here and minus PR. So, what is the QK? QK is nothing but the PK cos theta, and what is PR? PR also nothing but the PK cos theta, because this is the P and this is the K. So, angle is theta. So, what is the value over there? It is 0. But when you are talking about the rays 1 and 3, because they are into the same plane, so how we are getting? So, when the rays are coming over here, same thing we are doing, we are making the perpendicular from the K point onto your rays. So, here the ML plus LN. So, here the distance in between the K and L is small d, which is nothing but the interatomic distance. So, in this particular case how we are trying to calculate, this angle is also theta and this angle is also theta. So, now we have to calculate that ML plus Ln. So, ML is what? Which is nothing but the d sin theta, and what is Ln? Which is also nothing but the d sin theta. So, ML plus Ln is nothing but the 2d sin theta. So, scattered rays 1 and 3 will be completely in phase if n lambda is equal to 2d sin theta. So, now we are going to discuss about the scattering across the planes. So, here first let us consider the scattering across the planes. In this particular case you can see that we are having different planes over there. So, the path difference between the ray 1 and ray 2, which is nothing but the ABC, means AB plus BC, which we have already discussed that AB is d sin theta and BC also d sin theta. So, it is called the 2d sin theta. So, the path difference between ray 1 and ray 3, so it will be this one and this one plus this one and this one, that means 2d sin theta in multiplication by twice, that is nothing but the 2n lambda or maybe 2n lambda. So, this implies that if ray 1 and ray 2 constructively interfere, rays 1 and rays 3 will also constructively interfere, that has been proved. So, what are the notes over here? The number of diffraction order n depends on the glancing angle theta is increased, then n also increased. Number of diffraction order n is maximum when the glancing angle theta is equal to 90 degree. If n is equal to 1, that means first order of bright, that means angle theta is also means that first order of the glancing angle. If n is equal to 2, that means second order bright, or maybe angle theta is also meaning the second order of glancing angle. Now, we are going to discuss about the modes of scattering of X-rays on the crystal structure. So, there are 3 scattering modes. So, first one is called the scattering occurs in all directions and is weak, intensities add, which is nothing but the by atoms arranged randomly in space as in a monoatomic gas. Then we are talking about the second and third point. What the second point says? It says in a very few directions, those satisfying the Bragg's law, the scattering is strong and is called the diffraction, amplitudes add. And third, in most directions, those not satisfying the Bragg law, there is no scattering because the scattered rays cancel one another. So, by atoms arranged periodically in space as in a perfect crystal. Now, we are going to discuss about the difference between the diffractions and the reflections. So, diffractions means the diffracted beam from a crystal is built up of rays scattered by all the atoms of the crystal which lie in the path of the incident beam, whereas reflections of visible light takes place in a thin surface layer only. The diffraction of monochromatic X-rays takes place only at those particular angles of incidence which satisfy the Bragg's law. The reflection of visible light takes place at any angle of incidence. The intensity of a diffracted X-ray beam is extremely small compared to that of the incident beam, whereas the reflection of visible light by a good mirror is almost 100% efficient. Now, what are the conditions for diffractions? So, first, as previously already we have discussed, diffraction in general occurs only when the wavelengths of the wave motion is of the same order of magnitude as the repeat distance between the scattering centers. This is the first point. Second is that this requirement follows from the Bragg's law. Since sin theta cannot exist unity, we may write n lambda by 2d is equal to sin theta, which is less than 1. Therefore, n lambda should be always less than the 2d value, d is nothing but the interatomic distance. So, for diffraction, the smallest value of n is 1, sometimes n is equal to 0, corresponds to the beam diffracted in the same directions as the transmitted beam, it cannot be observed. Therefore, the condition for diffraction at any observable angle 2 theta is lambda is always less than 2d. Now, what are the applications of the Bragg's law? Experimentally, the Bragg's law can be applied in 2 ways. First is that by using the X-rays of known wavelength lambda and the measuring theta incident angle, we can determine the spacing d of various planes in a crystal. This is called the structure analysis. So, actually from these particular slides, we are actually starting the structural analysis of our materials. Alternatively, we can use a crystal with planes of known spacing d, measure theta and thus determine the wavelength lambda of the radiation used. This is known as the X-ray spectroscopy. So, now we are going to discuss about the diffractometer setup, the how it works actually. So, first it is having some X-rays tube which is nothing but the source of X-rays. So, in this particular case, this is the X-rays tube which is giving you the source of the X-ray. Then incident beam optics to conditions the X-ray beam before it hits the sample. So, we are having some kind of slits. So, through that slits the X-ray beams are coming and then it is falling onto the target itself. Then we are having that goniometer, the platform that holds. So, this is actually the platform which is holding our samples or maybe the materials. So, holds and moves the sample, optics, detector and or tube. Then we are having the sample holder which will actually hold the sample. Then we are having the receiving side optics to conditions the X-ray beam after it has encountered the sample. So, here we are having that receiving slits which is just again managing all the diffracted beam over there, and then we are having the detector to count the number of X-rays scattered by the sample. So, this is the whole setup of our XRD machines. Now, working of the X-ray diffractometer, the theta is the angle between the X-ray source and the sample, whereas 2 theta is the angle between the incident beam and the detector. So, this is the 2 theta, this is only the theta, and here is also, this is also only about the theta over there. So, now the basic functions of a diffractometer is to detect X-ray diffraction from materials and to record the diffraction intensity as a function of the diffraction angle, which is nothing but the 2 theta value. The X-ray radiations generated by an X-ray tube passes through solar slits which collimate the X-ray beam. So, here the focusing is going and then it is coming through the solar slit and then it is falling onto your specimens. Here we are keeping the specimens, then we are having some anti-scatter slits, through that the diffracted beam is going, and then we are having again solar slit, through that it is going to some diffracted beam monochromator, and then from that it is directly going to the detector itself. So, the X-ray beam passing through the slits strike the specimen, X-rays are diffracted by the specimen and form a convergent beam at the receiving slits before they enter a detector. By continuously changing the incident angle of the X-ray beam, a spectrum of diffraction intensity versus the angle between incident and diffraction beam is recorded. So, this is the working principle of that X-ray diffractometer which I have already discussed. So, from this particular, just you can see that how we are getting the peaks, because it is hitting our materials into different planes. So, like the D1 and then you can find the D3. So, here the when it is hitting, like it is known as the D3. So, a different angle it is hitting, and then after that we are getting the signals at the detector. So, now we are going to discuss about the diffraction pattern. So, generally after doing the XRD study, whatever the results actually we are getting, or maybe that whatever the graphs actually we are plotting, it looks like this. So, here a diffraction pattern from a material typically contains many distinct peaks, each corresponding to a different interplanar spacing, or maybe the D. For cubic crystals with lattice parameter A0, the interplanar spacings D, generally HKL, of planes labeled by Miller indices. Miller indices is nothing but the HKL, these all are the planes, are D subscript HKL is equal to A0 by root over H square plus K square plus L square. From Bragg's law, we find that the HKL diffraction peak occurs at the measured angle 2 theta subscript HKL is equal to 2 sine inverse in bracket lambda root over H square plus K square plus L square by 2 A0. So, now we are going to discuss about the almost the last part of this particular lecture is the XRD applications. So, generally we are doing the phase identifications of any materials, we can get the crystal structure determinations, we can get the radial distribution functions, we can get the thin film quality, we can get the crystallographic texture of materials, percent crystalline amorphous means percentage crystalline, whether it is crystalline, semi crystalline, or maybe the amorphous materials. We can get the crystal size of that particular materials, we can get the residual stress or maybe the strain of that particular materials, we can get the defects, that is also another beauty of that XRD study, we can get the defects inside the crystal structure of any material. We can get the in situ analysis, phase transition, thermal expansion coefficient, etc., and also last but not the least is that superlattice structure. So, now we can conclude our lecture like that, that in these particular lectures a overview has been given to you about the X-ray generations and using of the X-ray to determine the crystal structure and their defects by the Bragg's law. Thank you.